All right, everybody, welcome back. This is Unit 2, Topic 2.5, which is on natural disruptions to ecosystems. So, just kind of a quick review of a couple of things that we've talked about before. This whole unit really is about biodiversity, and we've talked about like individual, like genetic differences, for example, amongst like individuals of a species and how that can occur. We talked about mutation and genetic recombination, how that can create differences or changes in individuals. We also talked about changes in populations. For example, genetic drift or the bottleneck effect or the founder effect, how these things can kind of drive an entire population of organisms to change. But today, I want to talk a little bit about how a whole ecosystem can change. Obviously, this can be done anthropogenically. For example, this picture here, of a forest and a stream going down the middle. This can easily be disrupted by humans. Imagine, for example, that a logging company comes in and they want to just remove all the forest, all the trees. Think about the impact that that might have on the actual stream itself. One thing that might come to mind is all the organisms that live in the forest. A lot of those organisms are predators of, let's say, a lot of the fish and organisms that live in the stream. So, just by removing the forest, you're removing habitat. You're also kind of messing around with the food web, right? If you remove some of the predators, then a lot of the organisms in the stream will probably overpopulate. That could be a bad thing for the stream or for the community. Another thing that I guess that could occur is, this is something that we learned about when we saw the video about ecosystem services. Think about all the soil that those trees are holding, right? All the root systems are embedded in that soil, and all of a sudden you remove all those trees, and now all that soil becomes very erodible and it can just wash away, and all that dirt can get into the stream, and that can have a pretty big impact on the whole stream ecosystem. Another thing that we sometimes forget about, but this is kind of an important thing that trees offer, is shade. Just think about this area. Let's see over here on the left. Kind of this region right in here. I don't know, just kind of looks a little bit shadier compared to some of these other areas. Well, shade does something kind of important. It actually cools things down, right? So, this area of the pond might be much cooler than some other areas. So that could, just that abiotic factor of water temperature would be affected if we removed all these trees, and that could impact some living organisms that live in the stream as well. But just removing the forest, through an anthropogenic thing like logging, for example, it has a lot of repercussions on the actual stream. But this is kind of about natural disruptions. This topic. So imagine if there was a forest fire. Let's just say it was a natural fire. I don't know. Let's see, it was caused by lightning or something, and all the trees burned down. Well, you would still have the same effects on the stream, right? We would still lose all the shade and the habitat and the potential for all the soil to be held down. All of those impacts that we mentioned with a logging company removing all the trees, that could also happen through natural events. All right, so natural disruptions, do cause ecosystem changes. They're natural things that occur, and anthropogenic things can cause the same thing. The thing about natural is those things have been happening, for a millennium, whereas the anthropogenic stuff, that stuff has been occurring much more recently, and we have a much bigger impact because we can do things so quickly to an ecosystem. Anyway, now when it comes to these natural events, they kind of occur. It kind of depends on what type it is, I guess, but some can occur more periodically. Like for example, let's say there's a tides, like the high tide and the low tide. Let's say you're a starfish, or you're some kind of a sea star or something, and you're living in an intertidal zone. And normally throughout the day, there's like a low tide. Then all of a sudden, let's say in the afternoon or something, there's a high tide that comes in, and now all of a sudden the whole ecosystem changes, right? But the thing is about tides is they always occur, kind of regularly, right? They always kind of occur at the same time every single day, so we can kind of predict, when those things are going to occur. In Africa, they have what they call the rainy season and the dry season. For example, let's say the months of, I don't know, September to December. I don't know, let's say that that's the rainy season in an area of Africa, but that occurs every single year. I mean, those are periodic things that we just know are going to happen. Um, Now, episodic are a little bit more irregular. Probably one of the best examples I can give of an episodic disruption is something called El Nino and La Nina. These are massive oceanic changes. We'll talk a little bit more about exactly what they are and what causes them more in a couple weeks down the road. But in the Pacific Ocean, every 2 to 7 years, there's a major shift in like the currents that flow like through the ocean. And when this happens, it has a tremendous effect on global climate. It alters like how much precipitation is going to come down in certain areas of the world. It alters like average temperatures. The thing about El Nino and La Nina is, even though it happens every 2 to 7 years, it's kind of hard to predict exactly when it will occur. Is it going to happen every two? Is it going to happen every seven? Is it going to happen every four? So it kind of shifts a little bit. So it's not really easy to predict it in that sense. So it's not as regular per se as like a periodic disruption would be. And finally, we just have things that are just completely random, like meteors hitting the Earth, natural forest fires caused by lightning. Those things, we can't really predict them. I mean, we know that meteorites are going to hit the Earth, and they've hit the Earth before, but like, when is the next one actually going to strike the planet? We don't really know. We can kind of predict a little bit like how close they're going to come with like instruments and things like that, but like, when is going to be the next meteorite that hits the Earth? Kind of a random thing. Forest fires are kind of similar to that. Now, there's two general things that really affect these disruptions. As far as like their magnitude and their impact. One of them is the amount of solar radiation that reaches the Earth. This is something that, depending on where you live on the planet, right? I mean, you get a different amount of solar radiation. If you live the equator, for example, or you live up near the Arctic Circle, how much of that radiation actually reaches the surface, it kind of varies, right? And it's even varied throughout time. You can just look at the history of the Earth, and how it rotates around the sun, and even when meteors have hit the Earth and kind of knocked us out of orbit a little tiny bit, I mean, that has impacted how much solar radiation has reached the Earth. But that definitely affects natural disruptions. Another one is just the composition of the atmosphere. The atmosphere today is not exactly the same as what it was 100,000 years ago, 200,000 years ago, even a million years ago. And really good evidence of this is just looking at this graph. This is one that you'll most likely see again. Um, I think it's a really interesting graph, and it really, I think, kind of shows us the impact that humans have on our atmosphere. And this is showing us the amount of carbon dioxide in parts per million that's in our atmosphere. And it starts over here on the right with like present day, so like zero, and it goes back 100,000 years, 200,000 years, et cetera, all the way back to 800,000 years ago. We even have data that can take us further back than that. And you might be asking, well, how do we know like how much carbon dioxide was in the air, 800,000 years ago? And the answer to that is we look at ice cores. We actually drill, like in the Arctic and the Antarctic, we actually drill down and remove these big cylinders of ice that have taken, thousands and thousands of years to form. And we can actually look at the gases that are in those ice cores, and it gives us an indication of what the atmosphere was like, again, going back almost a million years. But just kind of looking at this graph, I mean, one thing that kind of sticks out is you can kind of tell that the amount of carbon dioxide in the air, for the most part, has kind of fluctuated over time, right? And kind of gets to a high point, kind of gets to a low point, and it's really kind of almost periodic, right? I mean, it's almost kind of like you just see this up, down, up, down, up, down. I mean, some cases it's a little bit higher of a magnitude than others, but I mean, it's almost like every 100,000 years or so, we kind of get a high point and a low point. And this just kind of continues. I mean, almost forever, right? All the way up to very recently. In fact, all of these low points that you see, like, for example, right in here, right over here, all these really low points, those actually indicate ice ages, where the amount of carbon in the air is so low that it actually causes the atmosphere and the planet to cool. When it gets really high, for example, at about 300 parts per million right here, that indicates that the planet's getting much warmer. Now, really, for 800,000 years, right here, this black dot was the highest that we had ever really seen. It was about 300 parts per million. But if you look at today, I mean, today we are over 400. And, people like always, this kind of irritates me. I get people who are like, well, the planet's warm right now, but it's been warm in the past, or yeah, there's carbon dioxide in the air, but there's always been carbon dioxide in the air. Well, yeah, that's true, but there's never been this much carbon dioxide in the air. In fact, going back, for as far back as we can even measure, we've never seen numbers this high. Remember, carbon dioxide is a greenhouse gas, and the more it builds up in the atmosphere, the more heat it traps in. So, I mean, our planet's getting warmer because of this gas that's building up in the atmosphere. Now, we can even kind of correlate that with ice melting. This is the Greenland Ice Sheet. Big country up there to the east of Canada, if you know where that's at. But Greenland is basically just covered in ice, and it has been forever. In fact, this graph here is just kind of showing us sort of about a 20-year span of the ice and what the ice levels are like in Greenland. This red line here kind of represents the global ice average, or the Greenland ice average, and it's measuring it in gigatons. A gigaton's like a billion tons of ice. So if you notice, like back in 2002, I mean, we were much higher than the average as far as how much ice there was in Greenland. We had almost 2,000 gigatons of ice that was above the average. I mean, there was just a ton. But you'll notice kind of what has happened to that ice since then. You'll notice, for example, these fluctuations, these up, down, up, down, up, down. Those are basically seasonal fluctuations, summer and winter. But you'll just kind of notice the trend. I mean, it is trending downwards. In about a 10-year span from 2002 up to about 2010, 11-ish, we went from 2,000 gigatons of a surplus of ice down to about the average. Okay, people might be like, okay, well, that's not that big of a deal. But look at the 10 years after that. It just kept on declining and declining and declining. So, about today, we're about 2,000 gigatons of ice less than our average over the last umpteen years. So, I mean, there's a reason why this keeps trending downwards, and it has a lot to do with this previous graph, right? I mean, as that carbon dioxide level is going up, the atmosphere is getting warmer, the planet's getting warmer, and then all of a sudden we're starting to see our ice melt. Now, okay, the ice is melting. Most people are like, well, big deal. The ice is up there in the Arctic, the ice is or down in the Antarctic or in Greenland, and big deal, right? Well, this does have a lot of repercussions on sea level, right? Ocean level. Here's, for example, showing us the Arctic ice shelf up here in September of 1984. You can kind of see how big it is. And these kind of white areas are areas where the ice is extremely thick. Okay, the gray areas are where the ice is a little bit thinner. And you'll notice over here in September, so the same month, in September of 2016, so this is like 20, 25 years later, whatever, actually 30 years later, you'll notice that it has really changed, right? I mean, not only has the volume of ice shrunk, but you see a lot of that white area is kind of disappearing. Now the ice is becoming much, much thinner. So, what happened to all of it? Well, it melted. Well, all that ice that melts goes into the ocean, and it should be no surprise that ocean levels are going to go up, which is what this graph is showing us. Again, we're kind of concerned, I guess, more of, I guess, if we kind of look at this area of the graph up here, this is the last 20 years. We can see that ocean levels have been rising, but that's been going on really all the way back. We've been measuring it since the 1800s. I mean, but again, the trend is that this is an issue. Global ice is melting, sea level is rising, and again, that all goes back to the carbon dioxide that's being built up in the atmosphere. Now, all three of these factors, temperature rising, ice melting, and then that what happens when all that ice melts, as far as habitat goes. This is kind of a positive loop. I mean, let's think about this. We've talked about negative loops, right? How they kind of go up and down, up and down. Well, think about this one. Okay, so not only is the atmospheric temperature increasing, right, global warming, but that temperature rise is causing the ice to melt, right? So it positively impacts ice melt. So higher temperature, more ice melt, right? But when that ice melts, one thing that I want you to kind of understand about ice, and maybe you learned this in chemistry class a little bit, right? Right, ice is kind of a whitish color, right? You see this ice in the background here. And we learned that, lighter colors like white, for example, reflect energy, like they reflect light, they reflect heat, right? The darker it is, the more it absorbs heat, right? So what you're looking at in this picture, this is ocean water, right? And this is the ice. So it doesn't take a genius to figure out that water is much darker than the ice is. So the water is actually going to absorb more heat. Well, if it absorbs more heat, that means the ocean temperature is going to rise, and that means more ice is going to melt. The more ice that melts, the more heat it's going to absorb, and the higher the temperature is going to go. So this is a positive loop. The only way that this is ever going to stop is if we stop putting carbon dioxide into the air, right? Because that's essentially what's causing this whole cycle, to continue. The only way to kind of get out of it is if we cool down the planet, and anthropogenically we're doing this. I mean, if this was a natural thing, I'm going to go back real quick to this slide. This is kind of what was happening naturally for 800,000 years. All of a sudden, you add us to the mix, and now look at what's happened to those levels of carbon dioxide. So we're the ones that have caused this problem, and we're going to have to be the ones that fix it. So, when it comes to environmental issues, probably the number one thing we have to look at is carbon emissions and carbon dioxide gases going up into the atmosphere to stop things like this from happening. Another thing that natural disruptions can cause a change in is something called migration. I think we kind of all know what it means to migrate, especially with animals. This is mainly a seasonal movement of animals, but there's a couple different ways that it can happen. One of them is what we call latitudinal. migration, which is when animals like move like from the north to the south, for example, or vice versa, I guess, depending on which direction they're going to move. Like birds, for example, flying south for the winter. Another type of migration is called elevation, where they like move up and down a mountain, for example, like during different times of the year for food or for water or whatever. Oops, yikes, what happened to my screen there? There we go. But again, I mean, a lot of birds and animals do this. Fish do it, for example. Salmon do it. Birds do it a lot, and it's mainly for food. Maybe for water. Like in Africa, a lot of those animals that migrate are for water. Mates, these crabs here in this picture. These are red crabs on an area called Christmas Island. It's in the Indian Ocean, kind of down by Australia and New Zealand, that area down there. Pacific Ocean, I should say, not Indian Ocean. Anyway, these crabs every year, thousands and thousands of them, migrate out to the ocean to mate, and then they'll come back in, and the whole island is like covered in these red crabs. Kind of an interesting thing, but it's mainly just for mating purposes. This is the monarch butterflies. Butterflies are kind of interesting. Their migration is kind of unique. They are an insect, not a bird, right? Butterflies. They were birds. Birds fly south for the winter all the time, and it's not that big of a deal. They're pretty well adapted to do that. But insects, migration of insects is much more difficult because, for one, insects don't live that long. For example, a monarch butterfly only lives, maybe a couple of weeks, maybe a month at most. But every single year, these butterflies make a 3,000-mile journey, from like the northern regions of Canada, all the way down to Mexico. And they can't do it, really in their own lifetime. Like, for example, let's say this monarch right here. Let's say he's going to migrate from up here in Canada. He's going to migrate down to Mexico. He might only, or she might only be able to migrate, let's say, down to Nebraska. That's as far as she can go because she's going to die. Well, she'll migrate, and then she'll probably breed, before she dies, and then she'll lay her eggs, like in Nebraska somewhere, and then she'll die. But then her eggs will hatch, and those caterpillars, which will eventually turn into butterflies, they will continue the journey. So they might migrate down to Oklahoma, and then they'll mate and they'll lay their eggs and they'll die. And then those caterpillars will turn into butterflies and they'll continue the journey. So you might get 3 or 4 generations of butterflies that actually make this journey eventually to Mexico. But I mean, it's kind of an interesting migration. Now, the problem with these monarchs is, they depend on a few steps along the way, a few stops before they get to Mexico, and where they stop is mainly where there's a certain type of plant. It's called a milkweed plant. These these insects are extremely picky about where they lay their eggs, and the reason why is because the milkweed plant provides a couple of interesting things for the caterpillars. One, it provides food for them. So it's not like they can't eat something else, but when they eat the milkweed, there's a chemical in it that's actually a poison. It's a toxin, but it's not toxic to the butterfly or the caterpillar. It's actually toxic to the predators that eat the caterpillars. So this milkweed is like super duper important, not only for food, but it also kind of gives them sort of a defense mechanism against their own predators. So the problem is that the butterflies are losing a lot of this habitat. In some cases, it's because of natural disruptions like forest fires and things like that, but it's also because of anthropogenic things as well. Like we're building, neighborhoods over where these monarchs normally would lay their eggs and where all the milkweed might be at. So you can see up here in this picture just the declining amount of area where these monarch butterflies can get access to milkweed. So that's becoming kind of an issue for them. Another animal, I guess, kind of that we hear a lot about is polar bears. When it comes to natural disruptions, for a polar bear. I mean, ice like up in the Arctic that we saw on that graph. There's always been ice that forms and declines. It forms and then it recedes. And we have this fluctuation for 800,000 years. And polar bears have always had to been able to adapt to that. Sometimes there's more ice, sometimes there's less ice. But think about what the polar bears depend on the ice for, right? It's not like the polar bears you know like live under the ice. I mean, they live on the ice, right? And they depend on that ice for food. Um, especially seals. Seals that pop up through these holes in the ice. The polar bears wait for them, and then they snag up a seal, and they can feed their cubs with it. They can feed themselves. They've been kind of depending on that for thousands and thousands of years. Well, now with all the ice melting, and again, we can see it graphically here how much ice they're losing. We saw the picture of the Arctic ice shrinking before as well. That's leading to a lot of problems. You know, um, not only is their habitat shrinking, but because that ice is receding so much, they're having difficulty finding food. So they're literally starving to death. Even gotten to the point now where polar bears have invaded, areas occupied by humans. They've migrated, away from their ice because they can't find any food. So they'll go into towns and places like that, to look for food. And now, when they do that, humans look at them as like pests. So what do you do to get rid of a pest, right? You kill it. So a lot of times these polar bears get shot or trapped or whatever, and they don't survive. So, there's a lot of factors that are going into why their habitat is shrinking. But the bottom line is it's, again, all tied to climate change, right? And it's more than just a natural disruption in this case, it's more of an anthropogenic thing. So, polar bears, they will probably, unfortunately, be gone in the next 50 years unless something's drastically changed. But again, that's for your generation to figure it out. I'm going to be dead. So, my generation and previous generations screwed it up enough for you guys. You guys are going to have to take control and figure out how we can save the climate, save the planet, save things like the polar bears. It's pretty important. So it's good to learn about this stuff. All right, guys, that's it for me for today. I will see you soon. If I ever can log off of this thing. Here we go.